Y luego de ahí, la paleta, otra.
7.5.
Entonces, payaso.
Okay, so we got a whole hodgepodge. We got 5 of the 6 trig functions all in play at the same time. So we either want to go to sine, cosine, or secant, tan, I would say. The problem being that cosine is easily convertible to secant. It's a reciprocal. Cotangent is a reciprocal of tangent. But sine, yeah, not easily converted to secant or tangent, right? So we've converted everything to sine and cosine. So we're going to say this is sine x over cosine squared x. Is that right? 1 over cosine is a sine over cosine. You multiply those. This is cosine squared over sine. That's the reciprocal of this, isn't it? Yeah. That's equal to sine x. Okay, so we got it in terms of 2 trig functions. We'd like to have it in terms of only sine or only cosine. You see we got these 2 cosines running around, and they're both squared. So that looks like a good candidate for the Pythagorean identity, huh? Should we first, yeah, you know, okay, so if we multiply both sides by sine x cosine squared x, then what values are we not allowing? Right, so I'm multiplying both sides by the same thing, right? But I have to say sine is not 0, cosine is not 0, so x can't be any multiple of pi over 2, right? That's, you know, north, south, east, and west. Not equal, sorry. Yeah. So I'm sort of disallowing those. But are any of those solutions to the original equation? No, right? Because this would be 0 or that would be 0. And so neither one can be a solution to the original equation. So we're kind of safe in multiplying by those and then making that caveat that, you know, x can't be any one of those. So then what do we get here? We get sine squared x, and sine cancels out. We get cosine to the 4th. Oh, really? X. And here we're going to get sine squared cosine squared. All right, so we got rid of the denominators, but we still have both sine and cosine. So we'd like to either get all sine or all cosine. At this stage, either one, I guess. It looks like kind of maybe sine is 1 minus cosine squared. So now it's polynomial and cosine, right? And our good old friend, the polynomials, come to bear, right? 1 minus cosine squared x times cosine squared x. So it looks like we're going to have a negative cosine to the 4th on both sides. That's good, isn't it? That's true, isn't it? Yeah. So, in fact, it's going to be simply 1 minus 2 cosine squared x equals 0, isn't it? Because I'm going to end up with a negative cosine to the 4th here. I can add cosine to the 4th to both sides, and those go away. Then I'm just left with cosine squared on the right, which I can subtract from both sides. And then I see that, sure enough, cosine squared x has got to be a half, right? Which means that cosine x could be plus or minus square root of 2 over 2. And where is that true? Here, 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 and here, right? This is positive square root of 2 over 2. This is negative square root of 2 over 2. These are, you know, the inscribed square, right? So this is pi over 4. And looks like we get, pi over 4 plus any any multiple of pi over 2, huh? So if I write, this is a right angle, this is a right angle, and this is a right angle, and that's a right angle. So if I start at pi over 4, and notice how I'm just using the geometry of this, where the solutions are, rather than saying, well, x could be plus or minus pi over 4 plus any multiple of 2 pi. I mean, that'd be one approach here, right? X is equal to plus or minus pi over 4. That's, yeah, or 3 pi over 4. Right? And how does that come about? Well, if you're solving cosine is negative, then you're in the third or the fourth quadrants. Yeah, plus 2 pi k, or x equals plus or minus 3 pi over 4. That's going to be here, where x is negative. In the second or third quadrants, what did I say before? Yeah, right. So the second or third quadrants, plus 3 pi over 4 minus 3 pi over 4. And then anything coterminal with those, which you could then somehow boil together. But if you just look at where they are, I think it's easier, right? Just say, look, I got pi over 4, I can add any multiple of pi over 2 to that and get my solutions that way. Get a single line instead of 2 lines. And you see that's all 4 solutions? Rather than saying plus or minus this and plus or minus that, and you think terminal with those. Oh, did I say plus or minus 2 pi k? That's true, but k could be negative, so that's kind of redundant. How are we doing? Yeah. So that came out pretty neat, despite the initial opaqueness. Opacity? Density? Okay, so that was 34. How about 38? So they say finding the intersection points graphically. They say graph f and g in the viewing rectangle and find the intersection points graphically, round to 2 decimal places. That's part A. And then part B, find the intersection points of f and g algebraically. Give the exact answers. So, okay, well, we've got 2 functions. We've got f of x equals sine x minus 1. So that's sine x shifted down 1 unit, right? And we've got g of x is, this is number 38, cosine x. That's just cosine x. Okay, so they say do it graphically. All right, well, should we graph cosine? So pi over 2, pi, 3 pi over 2, 2 pi, huh? Cosine goes through 1. Yeah, that'll work, huh? Yeah, shift it down 1. So here's negative 1. We're going to need negative 2 actually here, right? This is the y-axis and the x-axis. And cosine goes through these points, right? Just plot those 5 points and then draw a sinusoid through them like that. So that's g of x. F of x, well, that's going to be the sine curve shifted down 1, right? So we start at equilibrium. We go, oh, there's a point of solution. Back to equilibrium. Oh, there's another point of solution. Another one here. And we see this is g of x, huh? Oh, sorry, yeah, this is g of x, this is f of x. So it's pretty clear from the graph that we have a solution at pi over 2 and a solution at pi. And then that's going to replicate, right? It's a little sloppy. But yeah. So add any multiple of, so from the graph, x could be pi root 2 plus any multiple of pi, 2 pi k, or x could be pi plus any multiple of 2 pi, which is going to be any odd multiple of pi. Right, when you factor out the pi, you get 2k plus 1 there, or 1 plus 2k. I prefer to write 2k plus 1. That's then readily recognizable as an odd multiple of pi. So it's not true at 2 pi, but it is at pi, and it'll be true again at 3 pi and 5 pi and 7 pi. So these are the solutions from the graph. What if we try to solve it algebraically? Would we get the same thing? And this is, so we see that we have the unit circle approach. We have the laying out the horizontal, the angle on a horizontal axis approach and graphing things. And then we have, g of x, well, it says that sine x minus 1 equals cosine x.